reversibility, so going back and forth across the tipping points, and the rates of resilience of them.
Yeah, there's in the current formulation there's no hysteresis in that predicted transition. You can go backwards and forwards and you'd follow the same sequence of macro states, if you like, but it's known from maximum entropy applications to statistical physics itself, where particularly you have systems of interacting components, that the phase transitions that emerge from those systems do exhibit hysteresis and irreversibility. The Bose-Einstein condensation is a very pathological transition which emerges purely from the statistics in an ideal gas with no interactions, or in this case where the individual patches making up the system don't affect each other. But yeah, the Maxent does predict in other situations hysteresis.
I was really intrigued by the generalization of the statistical physics to environments. I thought it was a really nice approach. I have this nagging concern that there is an assumption in the statistical physics which you're carrying over here, which is that the statistical physics only really works for a uniform, non-structured gas. So here, I am wondering if the approach only really works for uniform landscapes. So something like a savanna, yes, it's not perfectly uniform, but it's much more uniform than something like the landscape of the UK, which is very structured. So I wonder if that structure is going to cause problems for the sort of statistical physics analogy.
It's true that the particular application of Maxent I presented does not have any spatial structure in it, simply because I represented the microscopic state, or the most detailed representation of the state of the system in terms of the abundance vector, so it's already an aggregate description. However, there's nothing to prevent Maxent being applied to spatially explicit microscopic states. That's done in statistical physics, where you describe spatially explicit arrays of magnets, for example, little magnetic poles in a two-dimensional or three-dimensional explicit lattice with spatially explicit nearest neighbor interactions, for example. There's no logic in Maxent itself which precludes it.
So all of those discrete parts in statistical physics, so they all have the same set of boundary conditions and behaviors, right? So I mean, there's nearest neighbors in that magnets example, but they all obey the same fundamental behavioral characteristics, the same laws, whereas that's not necessarily true for different types of landscape within something like the UK, where you have different parts of the landscape will obey different behavioral constraints.
Yeah, okay. Look, you can generalize to those non-uniform cases. I don't want to get too technical, but in the physics literature there's things called spin glasses, which are random magnets where the interactions are not uniform but actually random, plus or minus. The general idea I'm trying to present here is that Maxent does not predict the land use in this particular place. That would be like trying to predict the outcome of an individual toss of a coin. It's only predicting the frequency distribution, so it's not competing with agent-based explicit models. It's complementary, so it's restricted in what it can do.
Richard, when you mentioned about the Bayesian approach for dealing with the uncertainty, what's the prior distribution to use? The prior.
What were the priors? So we took the values in the literature and used were doubled or half.
you use any historical data or other additional data to influence your pride, or you just use informal to pride? That's not clear for me. What sort of pride you use? Yeah.
Sorry, what was that
Could you
question?
say that again?
Okay. I mean, when you basically you're talking about Beijing influence, the Beijing approach for dealing with uncertainty. I wonder, what sort of pride distribution you use, for the model and the parameters.
Yes, so for each parameter, there was a value in the literature, except for maybe one or two. Of course, these. Basically it's a model coming out of physiological ecology. So in almost every instance, the things like the Bertalanffy growth coefficient would be known, or we could calculate it from data. And so we had something from the literature, and our prior was a log normal distribution going from the value to double or half.
All right. Okay. Log normal. You know that?
And each parameter is independent of its prior.
The priors were all independent, yeah.
Okay. Oh, okay.
I just want to just ask my own interest about Maxent again. So you're saying that you get, it's not spatially explicit, you get a kind of a general distribution of how the land could change. So how do you think then you would link that, for landscape decisions? So how would you then link that to understand, in North Wales it now might be a good idea to convert grassland to forest or something like that, or that's a good area to do it. So to transfer it into the decision making process, I suppose, for policy.
There may be some questions which it is not tailored to do. I guess it's really tailored to predicting the distribution of land cover that would be the outcome of making some landscape scale decisions, assuming that not everybody is going to do exactly the same thing. So there'll be some diversity of reaction to a government policy, for example. And the logic of Maxent is saying that there'll be a diversity of responses, and it's sort of predicting the most likely response. So from that, you then could assess what would be the landscape scale consequence of that, based on averaging over that predicted distribution of responses. So it's a very sort of aggregated picture. As I guess as soon as you start trying to ask very specific local questions, then it doesn't really apply anymore, because the more detailed, the more microscopic, if you like, you go, the more you're asking, like, what's this molecule doing at this particular time, and the logic of Maxent no longer applies. It really applies to sort of large scale, maybe national or large regional decision making, where you're applying regional constraints or national constraints, but it's not telling this particular farmer in this particular corner of Wales what he should be doing.
But the sorry, just to follow up, I was just going to say, so the application. So I kind of think about, I do lots of energy system models, and they're kind of national scale, and they want one number and stuff. So actually, I think it would be right to say that this could actually be quite a useful tool to get a kind of introduce some heterogeneity, I suppose, into inputs, or understanding policy outcomes at kind of a national scale again, and then we can start to worry about where specific changes might occur. Yeah. Okay. Thank you.
So I was just going to follow up on that question. So am I right in understanding that it could possibly be quite useful to use something like the Maxent approach for understanding the behavior of the system, really? You're sort of trying to figure out what are the key things driving it. I suppose if you know that, then you could feed, if your aggregate response is somewhat similar to reality, then I suppose it gives you considerably more confidence that those are the key variables to then feed into more specific models. Is that what you?
That's correct. So in the same way that we identified water balance as the key driver for savanna, we weren't denying that fire and herbivory are key drivers for the diversity that you see. It's simply that we didn't need to model those processes explicitly. We treated them as random noise. So by analogy, we're sort of trying to do the same thing. But really, I'm sitting here, I shouldn't give the impression that I've worked out actually how to apply this to landscapes. I'm offering, this as a question, as a challenge for you to tell me, for example, what are the key constraints I should be thinking about socio-economically, for example. Where's the data that the patterns that I might be looking at to explain, to ground my model on. So it's really a challenge for you to help me.
I'm trying to think about the assumptions that get you to what you said, which is that you cannot argue with Maxent given the boundary conditions, and trying to apply that to land. And I don't know if I'm right, but you would have to assume that every parcel of land, however you think about that, whether that's a farm or something else, behaves at random according to some distribution, and they all behave at random according to the same distribution. And then of course Maxent will, given suitable boundary conditions, give you kind of the frequency distribution. But that assumption seems super strong in the land.
Maxent applies in that particular example to the abundance vector, which is just the number of patches of a given vegetation cover type, and it doesn't make any assumption about whether individual cover types have a particular distribution, whether it's the same. That emerges from Maxent. You don't really make any I don't know whether you don't make any assumptions in Maxent other than what's in the constraints, and so the probability distribution that comes out is entirely in information theory terms encapsulates only that information in the constraints, and it's the sort of least biased one that comes out.
Still the sort of inherent randomness.
Yeah.
That is assumed in order to have a frequency distribution in the first place.
Yeah.
That inherent randomness must be coming from the behavior of the individual thing.
Yeah. One shouldn't think of it, take the inherent randomness too seriously as actually what's happening. We know that in reality there are very good local reasons why this particular farmer does this particular thing, and there's all sorts of contingent reasons for that micro decision. What we're saying is that we don't deny there is an underlying determinism to all of these decisions. We're just suspending our way of representing that detail and saying, does the large-scale distribution can it be explained as if those micro decisions were like random coin tosses? In the same way we know the actual result of this coin toss depends on how fast my thumb was flicking it, and the wind coming through the doorway, and the properties of the table. It's not random in reality, but it's in the large statistical sense it can be treated as if.
But you do assume that all the coin tosses are the same, and that's the I don't mean whether randomness exists. I mean you have to have that similarity.
That's true in that the trials, whatever you want to call them, are assumed to be statistically independent. So, but the outcome or the measurement that you're taking in any given trial could be the measurement of a system which is highly coupled with interactions. So the independence assumption in Maxent refers to the independence of the trials in a sequence of trials, not in the statistical correlations within the system itself.
Yeah, so I find this very interesting and also kind of so absolutely opposite to the way we normally model things on the land surface, as you know, which is to basically imagine that everything we see, every bit of a spatial difference is somehow deterministic based on local conditions or local behaviours or whatever. So what really interests me about this is that we might use it as a way to sort of identify places where there is something special going on. It comes back a bit to Lex's point actually about looking for things that aren't fitting with a principle like Maxent. So you might imagine, I might imagine Maxent applies best at the large scale, like you said, where there's a kind of global constraint, maybe there's a total money going into farming or the total market or something like that. But as you get to local level, it won't apply, right? Because there's a place here that you're assuming is just as productive as a place over there, and it's not. But that means we have, in principle, a way to almost separate out the interesting stuff that's heterogeneous with this, don't you think? So imagine you just, because there isn't any information in what you presented, is there, about there's a good soil here or there's good rainfall here, there's just a domain constraint.
Correct.
Yeah, which is, I think that's the power of it actually, is that you can use it to identify where there are regional things that really matter. So it's a bit like saying how much of the apparent, how much of the spatial variability is actually Maxent variability, and how much of it is due to something else, like different local practices or different environments. It's sort of null model almost.
Yeah, it's a null model, which the key idea you get with Maxent is that the hypothesis you're testing is the division between the relevant drivers that are embodied in the constraints, and everything else, all the other dynamic details that you effectively treat as random noise. Now, it could be that soil variation could be treated as random noise because it's so variable and it contributes to the noise, but you don't have to model it explicitly in this procedure. And if your Maxent distribution faithfully reproduced the observed distribution, that would support that hypothesis. However, if your predicted distribution does not match the observed one, then the logic of Maxent says that there are other determinants in the system that you've not included, and then that might include geographical variation. So it's not cut and dry. This is just one application, but that you should bear in mind that the logic of Maxent and how you apply it is much more general and going through this cycle of observation versus prediction in isolating the key drivers.
I'm going to abuse my privilege and ask a question. So, if in the Maxent thing you have these random trials in effect going on, but if the probability in your savanna example of a forest next to a forest is different to a forest next to grassland, so you get mixes of higher probability, is that still going to work?
Yes, but though you would want that observation to come out as a prediction from the model rather than an input to the model. So rather than looking at spatial correlations and putting them in as constraints, I would put them that sort of information in say the water balance constraint, where I'm matching community water availability with community water use, and I would replace my community water use model, which just assumed all the patches were independent, like the water use of this tree is independent of whether its neighbour is grass or another tree or bare ground. I would then I could modify that to say that its water use depends on the presence of the other, and then when you apply Maxent to that interactive model, you get correlations coming out from Maxent as an emergent outcome.
Any more?
Just following on Peter's thing, I mean, we heard a lot about all kinds of ideas where decision making at the farm level was driven by economic rationale. I mean, let alone question whether there are other factors, but definitely, let's say the price you can get from growing wheat is a major factor here in the UK. Whether you will be an arable farmer or a sheep farmer. So if you think about this very simple parameter, different parts of the UK will have an average because of soil and slope and rain, different profitability for wheat. How do you see linking that as, I'm replacing your rainfall with the wheat price that you can produce on that square grid? How could you link that to just the decision of whether being an arable or a livestock farmer?
I guess it was trying to move to do that when I proposed some economic constraint as an additional constraint on the environmental one. But to be honest, I don't know in detail how to do that, and that's what I would like to have a discussion about afterwards with people more informed on that than me. But just by blindly following an analogy with the rainfall constraint, I could imagine that you'd assign some profitability to each land cover type in the same way that you assigned some water use to each land cover type, and then you'd have an overall constraint, perhaps that somehow the economy of the system as a whole was constrained by some global demand or something, and then you could just add in that constraint. And the beauty of Maxent is the constraints combine additively in the analytical solution. But I don't know whether that's the best way of describing the financial constraint. But in that example, that would then bias the probability distribution that Maxent predicts towards land use cover types with higher profitability, for example, but would also predict variability around that, allowing for the fact that farmers are not just interested in probability in profitability, but are constrained by lots of other contingent factors. But I'd really like some input into how to formulate those kind of financial or economic constraints, or whether it's even possible.
I guess it becomes policy relevant when you're looking at what subsidies do to the land cover distribution, right? So I guess there might be a profitability associated with landscape, but you can tweak that around in principle as you can to death probably by saying I'll subsidise this and not this. And the question is, when would that, say you wanted to reforest, what would you need to do given those constraints? It would be a kind of zeroth order question, wouldn't it, to answer?
Yeah. So it's looking at the sort of top-down manipulation. What top-down manipulation do I need to do in order to achieve a certain distribution, rather than a sort of microscopic Maxwell-Demon type of intervention where you're looking at the microscopic manipulation.
Term policy and the manipulation.
Yeah, that's
You're clearly all looking forward to your lunch.
we are.
Can I just ask one of Richard actually? So you showed the MCMC miraculous effect, but you weren't sure why. Why it was so good? Is that what you're saying?
I think probably other Richard does know, but we haven't had time to explain to me fully.
Does anyone else know why that's so good? Is it always that good? So the data looked amazing.
Did they maybe use important sampling techniques which speed things up? I don't know. That could be. I'm not an expert, but those are used. I suspect something like that is done.
Right.
And those are great techniques for in loads of cases. Also, actually in StatMac, I think people use those techniques.
I think very highly parameterized MCMC models, especially ones that are kind of autoregressive and depend on previous time points to make predictions about next time points, do extremely well at modeling time series. They have done for a long time,
Right.
and they produce exactly that kind of bang on model. So I think it's a combination of the number of parameters you've got and the dependence on the previous time point or time points. So the biggest weakness that I've encountered with them is that they're somewhat sensitive to missing data, and their predictive power is extremely limited because of their dependence on previous data points.
Right.
So you can use them to do things like characterize parameters in the model, but what you can't do is use them, if there's a missing chunk of data, they tend to struggle a little bit about exactly what to do with it. and you obviously can't run the model forward into the future to make predictions, because you end up just amplifying everything and rapidly diverging from reality. But they're really great for pinning down individual parameters.
I think a problem at the moment is in actually using them, because there isn't any R code that you can just plug your model into. So Richard's trying to improve the R code that he has written, and then we'll of course make it publicly available. But I think it's still going to require some tuning, what Richard calls tuning. I mean, it's not going to...
All written in base R, or is it?
Hmm?
Is it all written in R, or is it leveraging C libraries or Fortran libraries underneath?
Well, we're getting a little bit technical here. What Richard has written is in R, but so the models that I use, it hasn't worked adequately on those so far. Those are written in NetLogo, which is a higher level language based on Java. And the problem is that because it does things sequentially, if it falls over at any point, then you've got big problems, and you've got to go back to the previous state. And that kind of difficulty means that in practice, research students in biology aren't going to use it, not until it gets a lot easier to use than it is at the moment. But I mean, there's great promise there, but it's difficult to know how to solve these implementation problems, because who's actually going to make the R code sufficiently robust that everyone, you don't get research grants for that kind of thing. So there's a little bit of a gap at the moment, I think.
I mean, I think there are steps being made in the right direction for speed in these kind of things. So, in my previous life as a sort of bioinformatician and more molecular biologist, there were definitely steps to use Bloom filters to speed up things like MCMC codes, and they, because once you can shift things onto a graphics card and use something like a Bloom filter, you can speed things up by hundreds or thousands of times. So it's coming. I think the speed is coming. It's just going to take time.
Okay, shall we thank Richard and Ronnie there?